How to design against buckling in engineering. Imagine a tall, slender column holding up a bridge or a skyscraper. If it buckles unexpectedly, the whole structure could collapse. That's why understanding how to prevent buckling is so important. Buckling is a sudden failure mode where a component deforms sideways under compression, often causing catastrophic failure. It's a common issue in many structures like columns, beams, and supports. To stop this from happening, engineers use several key strategies. First, increasing the stiffness of the member is essential. Stiffness measures how much a structure resists deformation. Using materials with a higher modulus of elasticity makes a big difference. For example, steel is stiffer than aluminum. Also, choosing cross-sectional shapes like I-beams or box sections increases the moment of inertia, which helps resist bending and buckling. Adding stiffening elements like ribs or flanges spreads out stress and makes the structure more stable. Second, reducing the effective length of the member is a smart move. The shorter the unsupported length, the less likely it is to buckle. Engineers often add intermediate supports or braces to cut down the length. Support conditions matter too. Fixed or continuous supports make a member less prone to buckling than pinned or free ends. Third, optimizing the shape and size of the cross-section plays a big role. The radius of gyration, which depends on the shape, influences buckling resistance. Larger radius of gyration means better stability. That's why I-beams and box sections are popular. They maximize this property relative to their area. Fourth, safety factors and buckling analysis are vital. Engineers use formulas like Euler's buckling formula to calculate the critical load a member can handle before buckling. They then apply safety factors, usually around 1.5 to 2, to ensure the actual load stays well below this limit. Modern tools like finite element analysis help simulate how structures behave under various loads, revealing weak spots before construction begins. Lastly, considering material and load conditions is important. Buckling only happens under compression. Engineers compare the applied compressive stress to the material's yield or ultimate stress. If the critical buckling load divided by the cross-sectional area is less than the material's maximum compressive strength, buckling will likely occur first. In real-world projects like building columns, bridge supports, or rail tracks, these principles guide design decisions. Adding stiffeners, shortening unsupported lengths, choosing the right materials, and verifying with analysis all help prevent sudden failures. Understanding how buckling works from a mechanical failure perspective shows why seemingly stable parts can suddenly give way under pressure. By controlling geometry, material properties, and support conditions, engineers create safer, more durable structures that resist buckling and keep us safe every day.